Today in science class, we're going to answer the question, why do things float? We're going to take a look at answering that question in the form of a lab activity. We're going to test certain materials, measure their mass, and then put them in water. When they go in water, they're going to displace and move some of that water. We'll measure the amount of water they displace, and we'll be able to calculate and or predict if something sinks or floats. Now, in order to do that, we need to make sure that we understand what buoyant force is. When an object is placed into fluid, it's immersed in fluid, it'll move some of that fluid out of the way. Here's what you're going to feel when, if you've ever gone swimming, you feel like you're lighter or you have a sense of weightlessness inside of that water. When you're in that water, when you're immersed in that fluid is actually pushing back on you. Now, buoyant force tells us that if an object is getting pushed back on more than that object weighs, it'll float. So if that water being displaced, pushed out of the way, is greater than or equal to the actual amount of mass that that object has, it floats. However, if that object has more mass than the force being pushed back on it, it sinks to the bottom. So we're going to calculate what that looks like and then be able to predict if something will sink or float. Density is the other factor that we need to make sure that we understand when it comes to something sinking or floating. Density is the amount of mass that an object has in a specific volume. How much stuff is in the space that that object takes up. If that density is greater than the density of the fluid that it's in, say if something is more dense than water, guess what? It sinks in water. If something is less dense in water, then it floats. So density, if it's more dense or less dense than the fluid it's in, will determine if it sinks or floats, and that's helped out and enforced by the idea of the buoyant force, that water actually pushing back on that object. Let's jump into our virtual lab, and then we'll use what we've learned on how things will sink or float, our predictions of sinking and floating, to build a ship ourselves that hopefully successfully floats. Take a look here on our Monday schedule. You can see that there's a link to this video that you're watching right now, and there's also a link to the Sink or Float lab that we're going to do. You would click on that and open up the virtual density lab. We're going to be able to test out and see what different types of items can float. I'll read through our instructions over here on the left hand side so that you can follow along with our activity. There's also been assigned to you a page that looks just like this and a copy that's made on your Google Classroom page to where you're going to fill in the information on this as we go through the activity. So here you have the different objects: wood, aluminum, plastic, lead, cork, steel, clay, rubber, candle. You would write those right here in this area. Then we're going to learn how to calculate the mass of the water, and make a prediction, and then give us a final analysis. Because once we've completed this and filled this out, we'll have a better understanding of how in which we can determine if something is going to float or sink. Back to our instructions. When an object is placed in a fluid such as water, forces such as buoyancy act on the object. Buoyancy acts against the weight of an object and pushes it upward. The upward force, called the buoyant force, opposes the downward force of gravity. Archimedes, a Greek mathematician, made an important discovery about buoyancy. According to Archimedes' principle, the buoyant force on an object is equal to the weight of the fluid displaced or pushed away by the object. Weight is the measure of the force of gravity on an object, and weight is determined by mass, the amount of matter in an object. Archimedes stated his principle in terms of weight, not mass, because scientists in ancient times were not yet aware of the idea of mass. Archimedes explains why an object will float or sink. If the object displaces an amount of water that weighs as much as or more than the object will float. For example, even though a beach ball displaces only a small amount of water, the mass of the displaced water is greater than the mass of the beach ball. This is why the beach ball will float. An object that has more weight and mass than the water it displaces, such as a rock, will not float. In this virtual lab, you will find the mass of an object using an electronic balance. You will then predict if an object will float by comparing its mass to the mass of the water displaced by the object. Let's try it out. Again, on this page, you're writing in what you're supposed to do. So with the first one, I'll go through it with you together, and then you'll be able to do the rest on your own. The first item is wood, so let's type in wood. Next item asks for the mass in grams. Now the instructions ask us right down here. It says find the mass of an object by dragging it to the electronic balance and recording its mass in the table. Grab the piece of wood, place it on the scale. Now notice this little panel comes up so you can't see if the object floats or not because you're going to make a prediction. It says 13.3 grams. If I go back to this, I'm going to write in 13.3 grams. Now it says mass of water displaced. Next it says read the graduated cylinder, record the table of the volume of water displaced. Drag the object above the tank and drop it in the water, and then record the amount of water that's displaced. Put it over here, drop it in, the water fills up, and we get this nice magnification on almost 15.5 milliliters. Sorry, we got 15.5 milliliters. Now remember, Archimedes' principle said if the mass of the water displaced is equal to or greater than the object will float. So here, this number is bigger than this number. My prediction should say float. Let's check. I'm going to predict float because there's more volume here than there is mass in that object. And 1 milliliter is equal to 1 gram in terms of its overall mass. I click on float as my prediction and then watch what happened. They take that away and it reveals to me that it floats. I was correct. I want to go back and make sure that I got that right in terms of my prediction. I predicted float and I was correct. Next one I'm going to do is aluminum. Grab the aluminum, place it on the scale. Aluminum is 5.6 grams. I would then type in here, aluminum, 5.6 grams. Now I need to place it in the water. Pick this up, place it in the water, and see how much water is displaced. Looks like we have 1 milliliter. 1 milliliter. Well, I'm just going to make a prediction without thinking of the math right now, and then we'll come back to check and see if my prediction makes sense. I've seen aluminum cans floating in water, and they're so light, aluminum's so light, it's got to float, doesn't it? Let's predict float.
In order for an object to float, the object must displace an amount of water that is equal or greater in mass than the mass of the object.
Got it. My mistake. I predicted float. The overall result was sink because this number, the mass of the object, was greater than the mass of the water displaced. The only way that the buoyant force wins is if the buoyant force is greater than the actual gravitational force that's pulling down on that object. Let's try another one to make up for Mr. Shane's blunder. We'll try plastic. Our piece of plastic we would label right here. Plastic was 4 grams. Take that piece of plastic, throw it in the water. It's going to move about 4 milliliters. And because it's equal, I'm going to predict that it will float. It says if it was equal or greater than, if this number is equal or greater than this number in the corresponding category here, it will float. Pick float. Boom, we were correct. Try one more. A piece of metal that is really, really heavy, obviously. Look, it says it's 20 grams. Lead, 20 grams. If I take that and throw it into the water, move some water out of the way, and it has almost 2 milliliters. Now here's how you read this on a graduated cylinder. The water line up here, it looks like it's the back of the cylinder because it's three-dimensional. You actually read this bottom line where it comes up on the side. It'll pull up just a little bit. You want to read right where that line shows up, and it's even. So we've got 1.8 milliliters, which is obviously way less than the same amount in grams, so I'm going to predict sink. Again, if this number is smaller than this number, it's going to sink. If it's equal, it'll float. If it's greater than, it'll float. But here, where it was smaller than, it'll sink, so I'm going to do that same pattern and predict it. I was correct on this one last time. We're going to say and see what happens here. We're going to predict sink. Boom, we're correct. Okay, now Mr. Shane did a number of these for you. I would like to make sure that you get to do some of this on your own and keep going with this pattern. So there are 1, 2, 3, 4, 5 more for you to do. 1, 2, 3, 4, 5 more spaces for you to fill in. Now this should identify and show us what Archimedes' principle is, but just for fun we're going to go ahead and put Archimedes' principle, the definition, down here, and you'll be finished with this portion of our lab activity. Class today is to apply what we learned in terms of how the Archimedes principle works. I want you to think about those huge massive ships that you may have seen on Lake Michigan right down the road, or maybe on the ocean. They're huge tanker ships or huge cruise ships. They're made out of metal. They're way too heavy to possibly float. However, because they're so heavy, because the shape of those ships, they actually displace and move more water out of the way, out of the bottom of the hull, than the ship weighs itself. Hence why it floats. We're going to try and take that principle into our own mind and understanding and develop something that is successful in floating as well. But to do that, we've got to figure out what's the best way to create something like that. If we were in person, we would be able to create these cool little tinfoil ships. Now, Mr. Shane has designed a number of them, so you can see the different types of designs, and we would then test out who could make the actual best ship and apply Archimedes' principle. Unfortunately, you just get to watch Mr. Shane have some fun, do this experiment himself. Now, I've got 3 pieces of tinfoil that I use that are all relatively the same size, so there's no favoritism to different types of design, even though they look different. I made 3 types of designs, and I'm going to use the same type of weights in water to see which one floats the best. Obviously, the one's going to float the best that has the best design to move water out of the way, to displace water out of the way, because then Archimedes' principle is going to be true. If it moves more water out of the way, that the weight is in the ship, it will float. If it doesn't move a lot of water out of the way, guess what? It's going to sink. I thought of how different things are designed in terms of ships in water and boats, and I came up with my cargo ship here. We're going to call that, it's kind of shaped like a cargo ship. I've got my canoe. Canoes are boats where 2 people are going to sit in here and row. Those float pretty well. And then I thought of, well, inner tubes. People sit in inner tubes all the time, so I made this nice round little inner tube type of boat here that we're going to put some material in and see which one floats the best. All right, so here we are in a science experiment. We've got our beautiful body of water right here in this plastic dish. We've got our 3 designs, and we've got our cargo. To simulate our cargo, I've got these heavy washers, these pieces of metal. They're going to hopefully weigh these things down and demonstrate for us which one of these is going to be best at carrying these materials. We'll start with the canoe. I'm just going to quickly add these together here, trying to make it float as long as possible, and carry as many of these as possible. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Oh, and we're taking on water. Canoe was able to hold 13 of those cargo containers. Let's try our inner tube. Now notice this stands out of the water a lot. That means it's not displacing a whole lot of water while it's in it. See how much it can hold. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. It's taken on water. The problem with that design was probably because it wasn't necessarily balanced. It was too far out of the water that allowed it to have this tipsy-turvy kind of reaction to it. Now the best one, the one that I predict is going to be the most successful, is the one that's actually shaped like one of those big, huge tanker ships or those big, huge cruise ships. Notice the bottom of it. The hull is really wide and relatively flat, so it's able to push a lot of water out of the way, where that buoyant force is able to push on a lot of surface area on the bottom of this ship. This is going to hopefully be successful and explain to us why these huge, massive metal ships are able to float. That buoyant force that is pushing on the bottom of the ship is greater than the actual weight on the ship, even though that seems like it's really difficult to understand because those ships are made out of metal. The amount of water being pushed out of the way actually weighs more than all of that metal that's on that ship, which makes it float. Modern engineering. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. I got a couple of these metal nails right here. Those are pretty heavy. Let's see if those can throw it in there. Okay, 29 washers. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 metal nails. How about the jar that those washers came in? Will it float with that too? Now that's a little bit too heavy, but you can tell the difference between how that object is perfectly shaped to create all sorts of this displacement to water, therefore having the buoyant force hold this awesome, awesome thing up. Science turns into technology, turns into that way in which we've engineered the world to work based on what we've learned from it. Your next part of the assignment is to complete the buoyant forces activity. You're going to read through the 2 paragraphs on that page and then answer the questions at the bottom based on what we learned today. Good luck. Back in with you to make sure that we've got this done correctly. You have to read through the 2 sections here. The left-hand side, the right-hand side, where it talks about Archimedes' discovery and changing the submarine density. And then you answer the questions down below. I'll read through those questions so I can let you know what you're supposed to look for in your reading, give you some context. Number 1 says, even though a brick weighs less than a metal hull ship, a brick in a bathtub sinks, but a metal hull ship in the ocean floats. Why? Maybe our experiment that we just did helps you to understand that the shape of the ship displaces so much water that it pushes back up and has a greater buoyant force than the actual mass of that ship pulling down in gravity. Number 2, what do you think the neutral buoyancy of a submarine is? Explain how you think it works and when it might be used. Now, neutral buoyancy is meant so that something doesn't sink or float. It can actually be kind of stuck right in the middle. An example is a fish. Fish don't sit at the surface or sit at the bottom. They're actually able to swim at certain levels within the water. Mr. Chain learned how to calculate or to complete natural buoyancy himself when he learned how to scuba dive when he was down in Jamaica. You've got to be able to regulate the amount of air that you have. It keeps you at a certain level all throughout. Submarines do something different, do something similar, which you're probably going to find that information in this portion on submarines. I would look within the context of this right-hand side. Lastly, it says, number 3, compare the directions of the buoyant force and the force of gravity on an object. Now, I wonder what that will determine. Compare the directions of the buoyant force and the force of the gravity. Which way does the buoyant force push, up or down, and which way does gravity push, up or down? Compare those 2 differences.